Hello, good morning everyone. Today, inshallah, we will be talking about the surface integral, Stokes theorem, divergent theorem, which will cover lectures 19 and 20. And those are the last lectures in our semester this year. Thank you very much for following us, and please, I will need you, as I told you in the previous sessions, I will need you to study this part. It's carefully. It's really very easy to go through. It's talking about the integration. As you can see, we did plenty of types of integrations, starting from the double integration, the line integration, and through Green's theory. We went also through triple integration, the surface integration. Today we will finish by a link between all of this, either between the double integration in some cases, and the way to go using contour integration or boundary integration. Also, we will use or see how we can skip from surface integration into triple integration according to the divergent theory. So today we'll cover a lot of very nice ideas. It will connect all the types of integration that we did go through in the previous lecture. I've already sent you the updated form from the PDF files containing these slides to your WhatsApp. Please go through it and please try to resolve the solved problems all together once more. It's really very important, as I told you plenty of times, use your pen and paper and start resolving these problems. I want to start with you by remembering the area of how to evaluate an area on a surface of certain quadratic. So area of a part of a graph of a function, z is given as a function in x and y, which represent plenty of surfaces, like a sphere, like a paraboloid, like a hyperparaboloid, like a conical section, or a cone, or something like this. That's over or above, that's over above the flat region D, and the flat region is defined by the intersection between both the function and the plan, or the z equal to f of x or y. It's really very simple. I can do that. I can find or determine the boundary as we talked previously, and I believe this part we did go through it at one of our lectures through triple integration. So after we finished the double integration, we did go through this topic. You will find it in the previous sessions that we took previously. So it's really very simple. All I have to do is to find the area by doing a double integration through the domain of the function, using the square root of 1 plus the partial derivative of f of x and y to the power of 2 plus the partial derivative of f with respect to y to the power of 2. Just performing this double integration, we will be able to evaluate this area. Now, I will need to talk with you about introduction to surface integration. The surface integration in general, it allows us to compute the integral of a function over a surface in three-dimensional spaces. So if you need to find the integration or the value of integration of a certain function around some surface in multivariable functions, this is the way how to do it. Of course, it has very important and enormous applications in physics, engineering, particularly in fields like fluid dynamics, electromagnetism, and also thermodynamics. So it's really very important topic. And it's really very simple too. Once you start to grab all the tools that's needed, you will find it really very easy topic just to go through it. Types of surface integrals, we have two types. We have the surface integral of a scalar value, and in this case you will be given the function, the scalar function f of as a function in x, y, and z, and all I have to do is to integrate across the service this function, which is f, x, y, and z. It's really very simple. With the s in the service element, as you know. The other type of this service integrals, it is the service integral of a vector field. And it determines the flow of a vector field, which is called the flux. So for a vector field, f, and it is defined, of course, we know what we mean about the vector field, which is the components of the function through ijk. The service integral the service integral computes the flux through the service or the flow of the vector field through the service. So it's just only integrating this vector field dot the ds or the as I told you, the service, the directed service element, and the by ds direction, we means the value of the service element times the normal curve, the normal vector to the curve. And we will see, or to the service, and we will see this in the new slides. So, services, the set sigma, which is a subset of RQ, is said to be service if there exists a function R, which is defined through its domain, that mapping or translating elements from R2 into R3. So U and V, RU and V, it's going to be moving stuff from R2 or making the linear transformation or a transform from R2 into R3. How it is going to work? R is U and V, and for R3 or the map or the images will be X, U and V, Y, U and V, and Z, U and V. So once more, let's reread it. The set sigma, which is the service, is said to be a service if there exists this sigma, it's called the service if there exists R, which is the direction, which is the function, that's responsible about moving stuff from R2 into R3 by this app. This is what's stated here. Okay, such sigma, we say that R, the direction, is a parameterization of sigma. If R is of class C1, also sigma will be of class C1. Of course, you know what's class C1, which means the function and its components are differentiable ones. Of course, we are talking about services at the main slides. Okay, as your main slides, these are the shapes. As you can see, this is Mobius, either Mobius, or this is another shapes in or services in 3D. Okay, so let f such that function that's mapping from R2 into R by continuous function, and sigma, which is the domain or the service, the part of the service, x, y, and z, which is given by x, y goes to d, and z as a function in x and y. This service can be parameterized by R, which is going to be u and v, and f in u and v. So actually, if I have 3 components, x, y, and we could get z as a function in x and y, that's going to be the case that we are talking about, as you will see soon. Also, a part of this, or an example on this parameterization, is the equation of a sphere in x, y, and z, where you can parameterize it using spherical coordinates by considering R is a constant. So, for a certain sphere with a constant radius, it can be considered R. But we used to say R, phi, and theta. Here I can change the variables to u and v, and it will be exactly what we are talking about, or the case that we are studying. So R, u, and v is going to be R sine v cosine u, R sine v sine u, where v is the angle between the positive z direction and your half lengths, and for v, it's going to be the other angle which moves you through the plane from 0 up to 2 pi, and all of this is written for you here. Here's u, which is from 0 to 2 pi, and the v, as I told you, from 0 to pi. So you will be covering the 3 dimension, considering R as a constant. So R capital I mean. So that's an example of, as I told you, a service in the 3D that can be parameterized by R2, which is U and V, considering R is a constant. Okay, the regular parameterizing or parametric surfaces, sigma is said to be a regular parametric surface of region F. We can find partial R, partial U, which is simply partial X, partial U, partial Y, partial U, partial Z, partial U, and also for partial R, partial V, it's gonna be the partial derivatives for the components of this function with respect to V, as you can see. So all of these two partial derivatives are continuous on the surface. So if you multiply, getting the cross multiplication of these partial derivatives or these components, I partial R, partial U, partial R, partial V, and that's what you can see here if you have R as the vector for this surface. So just differentiating with respect to U and respect to V will give you the normal vector on this surface, which we will use in the evaluation of the surface integration, as we already saw in the previous slide. So mainly if R is X, U, and V is X, Y, and Z, these are the components. That's moving R2 into R3, as you can see. And it is in addition D of the plan. We can now define the integration on the surface using a certain scalar function. So here if we have a scalar function f, x, y, and z, that's the element of the surface. I can integrate through this surface or evaluate the value of this function around this the surface that we are talking about. Of course, this integration through the surface can be integrated, can be changed to double integration simply by multiplying the function after being parameterized to u and v times the magnitude of the cross multiplication of the R component with respect to u and v, which is the n vector or the normal vector on this surface. So partial R, partial U, it's going to be partial X, partial U, partial Y, partial U, partial Z, partial U. And this is V for you to remember. These are the two components that we will get their cross multiplication. So here once more, so this is about the evaluation of this function on the surface by the idea. If you need to evaluate the area on this surface, it's going to be really, really simple. All I have to do is use the surface element, but considering the integrand equal to 1. Also, I want you to remember that this area issue is the one that we started by our lecture this morning, and we already talked it previously, and changing from the ds into the double integration dx dy. And this surface area evaluates the value of the integration or the area of integration of a certain quadratic above certain plan or above the given plan, and this is the relation that we are talking about. I believe we need an example now to connect these information. So once more, if I want to evaluate the value of a function, on a surface of certain quadratic, like a part of a cone, a part of a cylinder, a hemisphere, a sphere, or something. So we use the surface integration for scalar value, integrating through the surface, on the surface, for this integrand, which is given by this function. What we are saying is we can parameterize this relation into u and v. So it's really very simple, but this way in translating the surface integration into double integration, it's really very simple. All I have to do is to get f as a function in R, so replacing x, y, and z by their components in u and v. Now I will have to replace ds by the magnitude of the cross multiplication of the derivative of the R vector with respect to its components. So since R is a function, or it's a function in u and v, so I will have to get the partial derivative of R with respect to u, with respect to v, doing the cross multiplication and getting the magnitude, and then you will have your integration ready to be used. As I told you, we are indeed need to have just an example to gather up or to wrap up all of these information. Determine the area of the portion of the sphere. So I need to determine the area of a portion of a sphere. Area means that the integrand will be equal to 1, as we saw in this relation. Let's do it together. Okay, and it is above the plan of z equal to 1. Now I have, since it is above this plan, and I will need to evaluate the hemisphere of x squared plus y squared plus z squared equal to 4. Also, I have the luxury to use the double integration formula that we saw in the previous slide, and I will write it for you in a second. So, using, as I told you, using the surface area formula, which is the double integration, 1ds, here we go, it is the double integration of 1 times, if I parameterize it, the parameterization du dv. As I told you, it's exactly like doing the area, which is the double through sigma, which is the part of the surface, with respect to ds. So instead of doing through this, I will change it, of course, to be a double integration and get the advantage of having this cross multiplication. So it will be durable for me just to do the double integration, as I told you in the previous slide. But also for a surface given explicitly, so if I succeeded in getting z, I can use the ds instead of going through du dv by this formula directly, which we took just seconds ago. If you remember, or if you remark, from here I can get very smoothly that z squared will equal to 4 minus x squared minus y squared, which is going to be simply like z equal to the square root of a 4 minus x squared minus y squared. Now I have z as a function in f, x, and y, and will be able smoothly to evaluate these partial derivatives as we will see. Once more, our domain, or the part of surface that we are interested in evaluating, is really very simple. It is the hemisphere which is above this plan, which is at z equal to 1, if I didn't forget. And that's the photo from another side. So it's mainly, this is the sphere that we are talking about, whose radius 4 units. And that's the plan at z equal to 1. And we are interested in evaluating the surface area of the part above this plan, as you can see. Now, I can write the sphere as z equal function in x and y. Already did that, which is 4 minus x squared minus y squared. The upper hemisphere, it is the upper part. So we will integrate over the region of z is greater than or equal to 1. And so I will have to find or determine the intersection, the boundary of this disk, which is the intersection between our sphere and the plan z equal to 1. So in order to do this, it's very simple. All I have to do is to replace z by the value of 1 or greater than or equal to 1, which is the part above. So it's going to be 4 minus x squared minus y squared, which is greater than or equal to 1. Just to square in both sides, you will have 4 minus x squared. I will do it step by step for you. It's going to be 4 minus x squared minus y squared, which is greater than or equal to positive 1. Just moving the 4 to the other direction, then I will have negative x squared minus y squared is greater than or equal to negative 3. Here we go. Multiplying in negative, I will get this form, which is x squared plus y squared, less than or equal to 3. Now I have the boundary, which is x squared plus y squared, x squared minus, x squared plus y squared, which is equal to 3, that's for the boundary. But we are integrating on this disk, which is x squared plus y squared, less than or equal to 3. That's the integration as I told you. Now, After knowing all of this, as you can see, we started by evaluating the surface integral of an integrand equal to 1, the area of on the surface sigma, where 1 with respect to the surface element, which is ds. And we changed this, it's the same as the double integration with respect to the multiplication of the partial derivatives of r with respect to u and v. And also we can directly, as long as we can get z as a function in both x and y explicitly, so we can use this form directly. Of course, using this form of z, which is 4 minus x squared minus y squared, and changing the domain and finding that we will integrate through the disk x squared plus y squared less than or equal to 3. This is really very tempting, as we can solve it as we did previously by polar coordinates, as you will see. So now once more, as we will see, this is A. That's the element of the double integration part. Z stands for 4 minus x squared y squared. And the disk is x squared plus y squared less than or equal to 3. That's our domain. So now I will compute the partial derivatives in order to get these two guys. Still, remember that we have z, which is the root of 4 minus x squared minus y squared. So simply, that's z, and these are the partial derivatives. I will do it and for you, and then I will scratch it. Okay? If I have partial, if I want to get partial z, partial x, for example, it's very, very simple. So all I have to do is to differentiate first the root, which is gonna be 1 over 2 of the root of 4 minus x squared minus y squared, or instead considering 4 minus x squared minus y squared to the power of half, just differentiating. So I will move the half, then taking minus 1, so it's going to be a negative 1. Then all of this will be times the derivative of the function inside the bracket. And by differentiating the function inside the bracket, I mean the part that contains x squared, which is negative of a 2x. So just differentiating this guy will lead to having minus of an x over the root of 4 minus x squared minus y squared, cancelling these two guys together. And in similar manner, it will be exactly the same on the derivative or the partial derivative with respect to y, as we will see. So that's for the details of the evaluation. So it's going to be negative of x over the square root of 4 minus x squared minus y squared. Exactly the same, but with respect to y, the y component will appear. Now I will have to take these two components and start substituting in the square root. So now once more, I will square both of them step by step. So you will come to x squared plus y squared divided by 4 minus x squared minus y squared. And once again, I will start making this substitution. Just in a second, I will need now to get 1 plus, okay, x squared plus y squared divided by the 4 of minus x squared minus y squared. Getting a common denominator of this relation will lead to having 4 over, minus x squared minus y squared, and the denominator is gonna be a 4 minus x squared minus y squared plus x squared plus y squared. That will lead to cancelling all of these terms, and we will be just only by 4 divided by 4 minus x squared. I would like to write it this way, so it's gonna be 4 minus x squared plus y squared. This is gonna help me out why we are going to change into polar coordinates, as you will see shortly, because we are talking about circular disk. So this is the best option for us, just for the simplest to navigating through the polar coordinates. So now once more, I have x squared plus y squared over 4 minus x squared. That's the integrand will be just replacing this part, getting a common denominator, and now I'm ready to integrate. So I will replace the integrand by the root of 4 divided by 4 minus x squared minus y squared dx in the direction of dx dy. Of course, the domain will be within the disk, which is x squared plus y squared less than or equal to 3. So now once more, as I told you, I will do everything with the polar coordinates. Let's go to parametric coordinates. I'll choose polar coordinates, which are replacing every x by r cos c, y r sine c, and of course dx dy with the Jacobian as we did previously. It's going to be r d theta. So all I have to do now is just integrating for r squared less than or equal to 3. That's the domain. And this guy is going to be just only 4 divided by 4 minus r squared. Of course, dx dy will be changed by r dr d theta. The integration will be really very easy to do. As you can see, r for a closed disk will be moving from 0 up to root 3, and for theta from 0 up to 2 pi. That's the limits of your integration. The integration process is really very simple, because as you remark, this is going to be a 4 out of the square root. Actually, for this integration, I will write it just right here for you for the anal integration. It's 0 to root 3, and then you will have 2r divided by the 4 minus r squared under square root with respect to the r, which is really very simple to integrate. As once more, it's just only a 2 over r times 4 minus r squared to the power of negative half with respect to the r from 0 up to root 3, just multiplying in negative, and you will have a function multiplied by its derivative to a certain power. So integrating is really very simple. All I have to do is to add 1 on this power, which is going to be a half, and then divided by half, 4 minus r squared, as you will see. Then I will finish this integration by substituting by the boundaries, and finally I will do the integration in the theta direction. That's the details of how to integrate this function easily. So it's really very simple. As I told you, all I have to do is just to go through it step by step. So for the domains from 0 up to root 3, theta from 0 to 2 pi, that's the integration that we are talking about. So once more, as I told you, get for outside and start to doing. I will leave this for you just to complete it. So completing this double integration, we will be able to evaluate the surface area above the z equal to 1 for the hemisphere or the spherical part of the sphere, which is x squared y squared plus z squared equal to 4, as you saw. Back again to another topic, which is really very simple, and also it's very nice to see how this shape, which is Mobius strip or band, some books or some textbooks, they call it Mobius strip, others they will call it Mobius band. And you have very nice vids on the internet that's showing you the details of the Mobius strip, and if you have a normal vector or if you have a pen, something like bends or something, moving through this strip, how it moves, it's really beautiful. So I would agree, I would really recommend that you see those bits. So the surface was only one side. So for Mobius strip, it's just only a surface with one side. That's an introduction for the last parts of our course. It's very, very simple, and you would see. It's a surface with only one side. So usually for any surface, I have two sides, the outer side and the inner side. And as we usually, or as we are comfortable and logically, if this is a surface, a part of a certain surface, so the normal vector on this surface is going to be upward. And of course, the normal vector on the negative direction, it's going to be on the other direction. This is why it is important to know these definitions. For certain services, that's a special case where they will be mixed together. Let's go through it step by step. So, it is the service with only one side, as I told you. The Mobius strip in the service oriented, or obtained, as two sides of a rectangular sheet. Here is the explanation. If you have just a part of a sheet, something like this, so just give that a second. Let's do it together. I believe now it will make much sense. So if you have a strip like this is a strip of paper. If you try to connect it to be a belt, you will move it like this. So it's gonna be a part of a cylinder, as you can see. So it's just a part of a cylinder. Mobius, it means this is the A point and that's the B point. Just make a flip 180 in order to be able to put these strips. Here we go, just a second. $180, and you will be able just this is in a second, I'm sorry. Here we go. So the point B will be connected with point A, both together. And this is the shape that we are talking about, the belt that we are talking about. If you move around this belt, you will be moving from downside, from the inside to outside regularly, and you won't know the difference. And this is going to affect on the normal vector, as you will see. So once more, after we saw this, and you will see a couple of photos here, the Mobius strip in the surface obtained as two sides of a rectangular sheet, as I told you, as I show you, okay, such as piece of paper, are joined together in the opposite direction. If they had been joined in the same direction, it will be an elliptic cylinder, as we saw just seconds ago, and will be the result due to the Mobius strip. Here we go. That's the shape in the main sides, in the main slides. That's the belt that we are talking about. Look, this is point A and that's point B. Okay, that's at the top of this side and B at the bottom of this side. I will do a 180 degree flip in order to connect B with A. So I will make this twist, as you can see here. So B will be connected with A, and that's the result that you will see. We are moving from inside to outside through this belt. It has plenty of advantages in mechanical engineering and in moving in the moving parts of an engine or something. So once more, as we did exactly in a second, that's the Mobius strip, as you can see. The reason that we are interested, and those also are shapes, I hope it's clear for you what's happening. Here, the flip this is from upward, this is from downward. I believe this photo here shows to you the flap in these both sides in order to be connected together. As I was telling you, the reason that we did go through or we mentioned this issue because it's going to be a very good example on the difference between orientable and the non-orientable surfaces. And we need this definition, Mobius strip or band. We need it to be an example on the non-orientable surfaces, as you would see, and to link it with the existence of the normal vector that I spoke with you before we started this part. So for the orientable surfaces, all the orientable surfaces, if you can consistently define a normal vector. So it has a normal vector in one direction, which is upward, and it will stay like this. So a surface is orientable if you can consistently define a normal vector at every point, such that the direction of the normal vector varies continuously across the surface. Properties of orientable surfaces. You can distinguish between sides, like inside and outside, as we saw. If this is a portion of an orientable surface, you will be able to know the outer and the inside surface, or between the sides. Has a well-defined orientation. Okay, you can define a consistent direction for a surface integral, like the flux or the flow of the vector field around the surface. That's the main reason that we are taking, or we did go through the knowledge of this part. Okay, examples like the sphere, the land, like the cylinder, and these all have two distinct, clear sides, which will control or will give a direction, a direct direction for the normal vector field. So if I have a sphere that's at the various points, or the ds element, as you can see, these are the directions of the normal vector. If this is a plane, so that's the direction of a normal vector also. For the non-orientable surfaces, okay, it's a surface non-orientable if you cannot define a continuous or consistent normal vector between the outside and the inside. If you can see here, that's for this plan, that's the direction of the positive direction of the normal vector above this plan. And for the negative direction, it will be on the opposite direction, going down. But, and it will stay like this. It will be like this. Outward of a sphere and downward to the sphere, the two directions that we are talking about if we have a sphere. But for the non-orientable surfaces, the directions, it will be flat. Or you won't be able to define the outer and the inner, and the normal vector will be changing between the inside and the outside directly. As you can see, the properties of non-orientable surfaces, sorry, this is non-orientable surfaces, no consistency inside or outside, as I told you, they change. Cannot assign a global orientation, since they are not stable. Non-consistent normal vector field, as I told you. And of course, one of the obvious examples is Mobius band. And you will see here, okay, once more, the shape of this is Mobius